So in the last video, we saw that single qubit quantum gates are described by unitary matrices. In particular, if the input to the gate is psi, then the output from the gate is u psi, where u is a unitary matrix. I often call this a unitary action. We justified this on the grounds that unitary matrices are the only matrices which preserve length. To be a bit more precise about what this means, it means that if we have a matrix, let's call it M, which preserves length, meaning that m psi, the length of m psi, is equal to the length of psi for all psi, then that can only be true if and only if M is a unitary matrix. And what we did in the last video was we proved this in one direction. Namely, we proved that if M is unitary, then it necessarily preserves length like this. But what about the converse? In this video, we will prove the converse. In particular, we'll prove that if this length preserving condition holds, then M must necessarily be a unitary matrix. The video involves quite a bit more detailed calculation than the earlier videos, and you may need to watch it over to get all the details. In particular, I'm going to introduce a fair amount of background notation. The background isn't all, strictly speaking, necessary. It's slightly overkill, which is a bit unfortunate. It also can take a while maybe to get used to some of this notation, but over the long run it's really worth it. It simplifies your life quite a bit, and so I think it's worth going through all this detail. All right, so without further ado, let's suppose that we have a vector, psi. Been dealing mostly with two-dimensional vectors now, but let's just imagine that psi is a vector in some higher, well, any dimensional vector space. Then we're going to define a new object, also called psi, but now with the bracket in the other direction, which is a row vector whose entries are the same but complex conjugated. And this is called, so this was called a ket, and you're going to groan if you haven't heard this before, but this is called a bra. To make this the bra-ket notation, or the bracket notation. It was named that by Dirac when he introduced it, I think in the late 1920s. And so we often call this the Dirac notation, or the bracket notation, or bra-ket notation, or whatever you like. Key fact to observe, or a few facts to observe about the bra notation: it's related to the standard notation by the Hermitian dagger operation. So in particular, this identity is true, and it's easy to see that it's true. We take this column vector and we dagger it. How do we dagger it? Well, we take the transpose, so it turns it into a row vector, and we take the complex conjugate of all the elements. So we get exactly this bra. And another nice identity to note is that the length can be expressed in terms of this bra notation. So in particular, the length of psi all squared is equal to the matrix product of this row vector with this column vector. And that's easy to see. Well, what is this matrix product? It's just a star times a, or the absolute value of a squared, plus the absolute value of b squared, etc., etc., etc. And that is, by definition, the length of psi. So physicists, using the Dirac notation, usually simplify this a bit. They don't put the two vertical bars. They get rid of one of them and just write it like this. So that's a slight simplification, but it's well worth it. It really does simplify life in the end. All right, just a little algebraic result which can make dealing with bras and kets a little bit easier. The result is this: that if you take a matrix M acted on psi and take the dagger, so the corresponding bra to this new ket, the whole ket M psi, not psi, it's equal to the matrix product of the bra psi times m dagger. So if you think of this bra psi as the dagger of the ket psi, this is just telling you that when you take the dagger of a product, it's the product of the daggers, but with the order reversed. It's a useful little mnemonic. And this is a very helpful relation. I mean, it doesn't look like you'd be doing this all that often, but you'll be surprised. In fact, we'll see just a little application very shortly. It's easy to prove. In particular, well, the way to prove it is just to apply the definitions. So let's look at this left-hand side. Let's look at the jth component, and we'll show that it's equal to the jth component of the right. And by definition, the jth component of this is just equal to the jth component of m psi all starred, which is equal to, by the definition of matrix multiplication, now we do a sum over a new index, mjk psi k all starred, which we'll just take through like this, and that's equal to, we can, because these are all just numbers, we can move the psi over to the left to make this psi k star mjk, oh, excuse me, let me make this mkj star dagger. So I'm transposing the indices and turning this into a dagger, the star into a dagger. And that is, by definition of the matrix multiplication, just the row vector psi times m dagger, the jth component. So that was a little bit sloppy the way I worked through that, but hopefully it was all quite clear. And this is a useful identity to keep in mind. Okay, so what can we do with that identity now that we've got it? Well, we can combine it, this identity, with this identity for the length up here. In particular, we can use it to get a nice expression for the length of m psi in terms of, well, the bracket notation. So the length of m psi all squared from this formula up here is just equal to, well, m psi multiplied on the left by the bra for m psi, which we know from this result here is psi m dagger. So we're just rewriting stuff here, and arguably we're not doing very much, but it's useful to be able to relate these different forms of notation, and in particular, it's often actually more convenient to work in these terms here. Okay, so a little bit more background. This is much lighter going, I'm pleased to say. I'm going to introduce a unit vector, or a set of unit vectors, and they're called EJ, and the EJ is just the jth unit vector. So in particular, the first of them has a 1 at the top and zeros everywhere else. The second has a 0 at the top, a 1, and then zeros everywhere else, and so on. And just a couple of observations. If you let m act on the kth unit vector, it is, of course, equal to the kth column of m. This is a basic fact about multiplying a matrix by a vector. And so if you look at the jth unit row vector, ej times m times ek, you see straight away that this is equal to the jkth component of m. So this is a nice way of relating the familiar matrix components to the bracket notation here on the left. Okay, so that's enough notational background, more than enough notational background. Let's get back to the main event. In particular, what we're interested in is this result. Remember, we want to show that if m preserves lengths when it acts on any vector psi, then M is necessarily unitary. All right, and so to prove this, we'll suppose that it preserves lengths, and we're just going to analyze the matrix M dagger M. We're going to show that it is necessarily equal to the identity. And we're going to do that in two steps. The first is we're going to look at the diagonal element, so the jth element, and we'll show that that's equal to 1. And we'll also look at the off-diagonal elements a little bit later, and we'll show that those are equal to 0. And that's enough to show that M dagger M is equal to the identity, and therefore that M is unitary. All right, so let's look at the diagonal elements first. So this is equal from the last slide to EJ, M dagger M, EJ, which is, as we've seen, just the length of MEJ all squared, again from our earlier results. But because M preserves lengths, that's equal to the length of EJ all squared, and EJ is a unit vector, so its length is just 1. So that tells us that, as we were hoping, M dagger M has all 1s on the diagonal. What about M dagger M on the off diagonal? So when J, the jkth element, when J is not equal to K. Well, I'm not going to actually do the analysis which shows it's equal to 0. You're going to do that in the exercises, and it's pretty easy. But the way we do it is, well, let me just tell you the basic idea. We look at M's action on the following state, EJ plus a factor, which I'll come back to, EK. So basically we're looking at EJ plus EK and the action of M on that. So we look at the condition that this length, all squared, is equal to just the length of this vector here, without the M, all squared. And so it's easy to analyze the length of this vector squared. We can actually just work it out explicitly. And to analyze this more complex expression where you have the M as well, you need to do a little bit of algebra. But by comparing the two sides, you're able, in fact, to prove that this expression, this off-diagonal element, is equal to 0. So something I didn't mention or didn't talk about was this factor e to the I theta, where theta is some real phase value. That's included in there. It turns out that to actually prove that this is equal to 0, you need to consider a couple of different values for theta. That's just a little technicality. It doesn't complicate the analysis very much. Anyway, you'll see how that's done in the exercises. Okay, so that completes the proof of the result. We now know that the unitary matrices are exactly those which preserve lengths. In the next video, we're going to get sort of a lot more, well, it'll be a lot easier, not nearly as many details, and we're going to look at some really concrete examples of single qubit gates, going beyond the NOT gate and the Hadamard gate to look at other examples, not just sort of saying in the abstract all the unitaries. We'll actually write out what the single qubit gates are.